This video is slightly more technical and expands on the first introductory video. So let's recap on why it is so difficult to implement innovation on industrial process scale in the mining industry. Now, metallurgical processes are inherently dynamic on a microscopic level, and we process engineers are actually very constrained using macroscopic process control variables. So as we try and squeeze more efficiency out of unit blocks, eventually the physics and chemistry turn against us. Think about the concept of metastability. Then we all know that integrated process flows vary with time. So the concept of steady state operation is really a theoretical one. And then we have to deal with lower ore grades, more impurities, complex minerals and particle textures. Let's lump these under resource dynamics. And then there are the volatile markets, which are dynamic. Let's just call this business dynamics. So how does it currently work? Let's focus on a single operation run by some company X. Due to these highly integrated dynamic factors, the technical landscape needs to adapt rapidly, so the company bosses pressurize the engineers and metallurgists to get optimal plant performance, which leaves very little free time to analyze the plant data. In parallel to this, the process engineers at the head office conduct benchtop analyses of the financial impact of some decision based on the available data, but these analyses cannot connect all the dots because there is no consistent framework available to do that. So to mitigate the risks, R&D companies are subcontracted, but there is a lack of a single framework that can be used to direct a collective research effort. Finally, there are many young, bright minds at universities that can contribute to the industry. But how many of these post-grad studies come to fruition only after the project has already finished? So by developing an all-encompassing dynamic framework, the project information can be consolidated instead of just having reports scattered across a company. So each bit of information adds collectively to the benefit of the project and yields an extremely powerful tool to strategize and innovate. So how do we start to build a project from scratch? For this example, let's look at the whole ore treatment of some complex oxidized silicate deposit. The operation is lumped into clearly defined sections, starting off with a mining operation to get the run-of-mine ore to the process site. The ore is crushed, milled and blended. By the way, the mining operation, conveying of ore, stockpiling and blending are all dynamic operations that can be treated in similar fashion to pumping material through pipes and store inventory in tanks. Let's move on to the refinery part of the process. Here we have the leaching operation, where we create reactor conditions to break the ore lattice and release the valuable metals into solution. After removing the bulk impurities from solution, we separate the solid phase from the liquid phase using thickeners and filters. Finally, a high-quality solution of valuable metal is created and then plated using electrolytic cells. Now, since it will take a few months to create a complete project baseline model like this, let's just focus on the first leaching reactor block, which would anyway be the logical place to start this project, as it lies at a pivotal point in the overall process flow sheet. The first step is to select the leaching unit block. Our choice varies from high temperature pressure leaching to atmospheric tank leaching, vat leaching and then heap or dump leaching. This order represents high to low energy intensity operations, demanding consideration of milling, heating, chemical potential and other energies. And obviously also involves physical, dimensional and numerous capital and operating cost factors. If it is an existing operation, the choice is obvious. Alternatively, looking at the bigger picture, once a baseline project model has been developed, blocks may be interchanged to assess the metallurgical and financial implications of other process choices. The point here is that without having a proper dynamic baseline project model, this would be a very difficult task, because the different technical and financial implications are always so highly integrated. For our oxidized or deposit example, no gaseous oxidants are required, and the reactivity of the proton as the oxidant and the atmospheric conditions would suffice. Also, considering that we would probably want to control the leaching acidity, stir tank leaching would be a good starting off point. So for a start, we need to decide what level of detail is required for each block. This is what we refer to here as sub-block dimensionality. Now, our overall philosophy is always keep it simple and only add complexity where required. However, this is not a constant because the level of detail required always evolve over the project lifetime. Now, the simplest starting off assumption is to assume that our reactor is well mixed, which means that we average each bulk volume element over the entire reactor space. Now, for a heap leaching block, this simplifying assumption would obviously not suffice. Now we have to decide whether we're going to explicitly recognize a range of different particle sizes. The philosophy that we have followed in sulfide pressure oxidation projects to date is to ignore surface area for very fast reacting phases, but to include it for all the slower reacting minerals. Now, the moment we venture into the particular domain, we inevitably have to include some microscopic detail. Now, there are different levels of detail we could add. The simplest is to average the unreacted volumes over some predefined geometric shape, which then in turn allows us to describe the rate of shrinkage in a single space dimension. Now, in our composite ore example, we have this added level of complexity because there is little liberation to speak of since there's no flotation step. Remember, this is a whole ore leaching example. So by using any available mineralogical data such as modal analyses and applying some basic principles, we can describe the composite phase as the sum of the metal oxides K associated with the fraction of the lattice undergoing a rearrangement, that is Fx, and the balance represented by the oxides where the particle lattice is completely pulled apart by the leaching action. Now, this approach allows us to vary the mineralogical composition across the different particle sizes, which then in turn gives us flexibility to consolidate the experimental and actual plant data, whilst being consistent with the dynamic particle population balance. This is what we call our phenomenological approach to modeling and simulation, because our assumptions are based on sound theory, but to simplify and speed up the computation, we lump parameters together where possible and use measured data to regress their values. Going back to our high-level process flow sheet, it should now be clear that by capturing the physical and chemical dynamics of our pivotal leaching block allows us to dynamically link the complete flow sheet together. Looking upstream, by having mathematically captured how the minerals distribute themselves between the different size classes and how these minerals respond to the reactor environment in the particulate domain, allow us to make a physical dynamic connection to the comminution and blending operations, and even allow us to link the system dynamics as far back as a selective mining operation. Then looking downstream, by having mathematically captured how the different species move from the mineral lattice to the aqueous phase, allows us to dynamically connect everything that happens upstream to the efficiency of impurity removal and valuable metal recovery in the downstream section of the plant. A lot of information has been given in this video, so let's stop here. In my follow-up video, we show how the leaching block model is implemented and illustrate some basic simulation outputs from our silicate or leaching example.